A policeman saw a drunk man looking for something under a streetlight and asked the drunk what he lost. The drunk says, "I lost my keys." And they both look together under the streetlight. After a while, the policeman asks, "Are you sure you lost them here?" The drunk replies, "No, I lost them in the park." The policeman says, "Why are you searching here?" The drunk replies, "This is where the light is." For decades, this search strategy is employed both by drunks and neutrino hunters with no keys in sight and a few key insights. In 1916, Einstein published the second of his general relativity papers. 100 years later, using Einstein's predictions, we are at the precipice of weighing the last elementary particle whose mass is unknown. Isn't this old news? Don't we know all the fundamental particle masses already after measuring the Higgs boson mass? Well, yes and no. Looking at the Standard Model, we see 16 massive particles, quarks, leptons like electrons, and bosons such as the photon, plus the Higgs boson charted together in a table reminiscent of Mendeleev's periodic table of the elements, except in the case of quarks, bosons, and leptons. On the table there is no periodicity, no apparent ordering at work. 3 of the 6 leptons, which means small in Greek, particles that don't participate in the strong nuclear force, are the 3 generations of neutrinos, electron, muon, and tau neutrinos. As integral as they are to the foundations of matter, we are in the dark about their masses. A particle's mass is arguably its most distinctive property, so this lacuna is rightfully seen as an embarrassment for physics. That is about to change. Neutrinos change their flavor, their generation type, from one flavor to another as they sail through the cosmos. This phenomenon is known as oscillation. The 2015 Nobel Prize in Physics went to Taiki Kajita and Arthur B. McDonald for the discovery of neutrino oscillations, which shows that neutrinos have mass. Their work devastatingly refutes the claims presented in John Updike's poem, Cosmic Gall. Sorry, John, while they remain small, neutrinos do have a mass after all. Thanks to Kajita and McDonald, not only do we know the neutrinos have mass, their work gives us a lower limit on their masses. At least one of the 3 neutrinos must have a mass bigger than about 1/20th of an electron volt. Physicists use Einstein's relationship E equals mc squared to convert masses to equivalent energies. This is quite svelte. The next heaviest elementary particle is the electron, whose mass is 10 million times larger. Most importantly, these lower limits give neutrino masses give experimentalists thresholds to target. All that's left is to build a scale sensitive enough to weigh them. Neutrinos are generated in nuclear reactions, such as fusion and radioactive decay. The ultimate reactor, of course, was the biggest cauldron of them all, the Big Bang. Like light, neutrons are stable. Their lifetimes are infinite. Because, like light, there is nothing for them to decay into. Since it's impossible to collect enough neutrinos to weigh them in a terrestrial laboratory, cosmologists will use massive galaxy clusters as their scales. Sprinkled amidst the luminous matter in the clusters are innumerable neutrinos. Their masses can be measured using gravitational lensing, a direct consequence of Einstein's general theory of relativity. All matter, dark and luminous, gravitationally deflects light. Gravitational lensing effect rearranges photon trajectories, as Eddington showed during the famous 1919 total solar eclipse. Star positions were displaced from where they should have been in the sun's absence, due to the sun's warping of space-time. The light that should have been there was lensed. The amount of movement, the lensing deflection angle, told us the mass of the lens. What kind of light should we use to weigh poltergeist particles like neutrinos? There certainly aren't enough neutrinos in our solar system to bend the sun's light. The most promising light source of all is also the oldest and most abundant light in the universe, the 3 Kelvin microwave background. These cosmic photons arose in the same ancient cauldron that produced the neutrinos plying the universe today. The CMB is cosmic wallpaper, a background against which the mass of all matter in the foreground galaxy clusters, including neutrinos, can be measured. In 2015, the Planck satellite showed the powerful evidence of gravitational lensing of the CMB using a technique that is eventually guaranteed to detect neutrino masses. This technique, based on CMB polarization properties, will dramatically improve in 2016 and beyond thanks to a suite of experiments deploying tens of thousands of detectors cooled below 0.3 Kelvin at the South Pole and in the Chilean Atacama Desert. Neutrinos are also the very paradigm of dark matter. They're massive, they're dark, that is, they only interact with light via gravity, and they're neutral, all required properties of dark matter. While we know that neutrinos are not the dominant form of the cosmos' missing mass, they are the only known form of dark matter. After we measure their masses, we will use these neutrinos to thin the herd of potential dark matter candidates. Just as there are many different types of ordinary matter, ranging from quarks to atoms, we may expect that there are also several kinds of dark matter. Perhaps there is a dark periodic table. The hunt is on to directly detect dark matter, and several exciting upgrades to liquid noble gas experiments are coming online in 2016 and beyond. Perhaps there will be detections, but so far, the direct detection experiments have only produced upper limits. In the end, neutrinos just might be the only form of dark matter we ever get to see. The next century of general relativity promises to be as exciting as the first. Space-time tells matter how to move, matter tells space-time how to curve, said John Archibald Wheeler. We've seen what the curvature is. Now we just need to find out what's the matter. And where better to look for lost matter than where the dark is.